Hello, this is Minky for the homework 10 exercise 1. For this question, it led us to talk about those stochastic process. And the first, let me change color here. The first process is Poisson process. So Poisson process is the first process that we learn in that course. So definition is here, and it is the the probability of number of buses arrives in like those t hours, and the number of buses is equals to k, and the definition is here, and the expected value is equals to lambda t, and autocorrelation is here. So I think this question give us a example that we feel the mean value is reasonable because the longer time we wait, the number of buses is larger, right? So I think this is really simple for us. So let's go to the second process, that is Poisson increment. So Poisson increment is defined as here yt, and in here xt is the Poisson process from the last question. So the probability mass is equals to like here, and based on the Poisson process definition, we could get the Poisson increment here. And then the expected value is like also xt plus y minus xt here. That is yt, right? We change yt to it, and then we take the parameters out, and right. So this is also the expected value of Poisson process, that is the time interval is epsilon. So this is equals to lambda epsilon, and it equals to lambda eventually, right? And then we could discuss by those two situations, we could get the autocorrelation for the Poisson increments. And then here we have the Poisson impulse. Also, this is xt is our Poisson process, and Poisson impulse figure is like this. That is ct t, and also the mean value of Poisson impulse is equals to lambda, and since zt is equals to the when epsilon approach 0, the limitation of yt. So the autocorrelation is equals to autocorrelation of portion increments. So when this is epsilon approach 0, it equals to it. So that's how we get the autocorrelation of portion impulse. Then we learned semi-random telegraph. So semi-random telegraph is defined as it xt equals to 1 when k is even in 0 to t, when it is odd it is equals to -1. So I think this is in our homework, right? So well, we already know how to calculate those two probability mass, and it equals to these two expression here. And expected value is equals to that, and here we have the autocorrelation. I think we don't need to talk more about semi-random telegraph, since it already appear in our homework. And the next one is random telegraph signal. Random telegraph signal is yt equals to axt, and the probability that a equals to 1 and a equals to -1, they are the same probability. It's 1 over 2. So the expected value is equals to it, and we take a out. So here that is the semi-random telegraph, and it equals to 0. So the expected value is also equals to 0 here. And then also we have that should be right. And the mean value of a square is equals to 1. And here the autocorrelation of semi-random telegraph signal, so they are the same. Next is our random walk. Random walk defined as it x and t equals to ks minus n minus k times s. So k is number of head, n minus k is number of tail. So n is the total number of head and tails, and it equals to 2k minus n times s. The probability is this is our binary distribution, so they are same, right? So we could simply get the probability mass here, and the mean value is 0, and the autocorrelation is the minimum of n and m times s squared. The last one is linear process. winner process is defined as limit as approach 0 t 0 and approach infinity xt. So when the process is it's a kind of limiting process of random walk. The density is here. Mean value is equals to limit of winner not winner, what was the random walk, so it equals to 0. And also the autocorrelation, there is a minimum value of t1 and t2 times rpi here. So these are all the stochastic process that we learned in that course.